Multiple ways to approach this. The one way that you can kind of think of it from an algebraic approach is, what if we create an equation for each one? Let's say Ben runs at a rate of 24 feet per second. So his rate, or slope, is 24 feet. And then Jerry is running at 20 feet per second. However, Ben gives Jerry an extra 10-foot head start. So those are the two equations. And I don't know if you've ever heard of the DIRT formula. You ever seen that before? It's called DIRT, and the reason why, because it looks like the word dirt, but distance equals rate times time. So all that is just a linear model that if we know somebody's rate and then their starting position, we can create an equation for it. So you may have seen that before. That comes up in physics, I think, a handful of times. But what we're looking for here is find the time that Ben and Jerry will be tied. Equal spot, equal distance. So when are their distances going to be equal? That's when you set their equations equal to each other. And then if we do some algebra, if I subtract the 20t, I end up with 4t equals 10. We divide by 4. Equals 2.5 seconds. Now that's not the only way to solve this, right? And some of you maybe created a table. Set up a table and looked at Ben's distance that he ran as time went on, and Jerry's distance as time went on. This is kind of like a system of equations where you have two equations and two unknowns. Now I could also ask you, how far did they go? Right? How far did they travel to become tied? Well, to do that, now that we know the time, you can pick either Ben's equation or Jerry's, and just let's figure out what v of 2.5 is, which is saying, let's just take 24, double it. I think that's 48, 60, I believe. So that tells us that at 60 feet, Ben and Jerry are going to both be there at the exact same time. It's going to take 2.5 seconds to get there. Now what this is this is a parametric expression or equation hidden in context. And we can create that. We're going to actually look at that in a little bit here. Our goal today is to use that idea of parametric equations. That's what we looked at before. That's what you guys did with the pair deck, which, if you don't remember that, some of you didn't do it. This was the expectations for last Thursday's homework. And you can see I have a handful of people tried it, but not everybody finished it all the way. So we have, I'd say half the class did it, maybe. And of them, a handful of us did it accurately. But this was the problems is you had to make the table with parametric equations, and then we graphed that, and that showed us the curve of the function as it moved along. And then we dealt with the two equations and changing it into a non-parametric expression, so an expression that has x and y's in it instead of x with t. So that was the work that was expected to be done last week, and you should hopefully be semi-familiar with that. If not, we're building off of that here today. So let's take a look at what we got going on today. The first slide is the notes that you definitely need to get down today. Super important. You're going to need this for the test. So write this down. I'll give you a second to go ahead and copy everything you need. So let's set the scene a little bit here. Let's pretend that there's somebody right here, and a lot of the problems that we have are talking about baseball. So somebody hits a ball, right? So a pitch comes in, and this person hits the ball, and what happens? The ball leaves the bat at a certain angle. It's called an angle trajectory. It goes up, and then the ball's going to go. Now, does it move at a perfect linear line? No, it might go up, and then it's going to slow down, it's going to come back down, and it's going to be more hard. But what we're going to do is we're going to use this idea of the fact that we kind of know a handful of things already about vectors. So we're going to take this idea about a vector and apply it to the vertical motion. So there's two things we need to know here. When we talk about theta, right, this is the angle that the ball leaves the bat, or it's the angle that something is thrown, or it's the angle that something is dropped. So that will be given, and it's usually in degrees or radians. And then the other piece that we really have to be well connected with is when we learn vectors, okay, we knew the magnitude, right? We found the magnitude of the vector. That's with a symbol that's over the v. Well, what do the absolute value mean? The absolute value is talking about your speed or velocity when it's positive. Speed is just the absolute value of velocity. So if you don't absolutely have these two down, I would write those down in your notes as well. Because when we read through each expression, we're going to have to be able to identify those. Well, apparently that's not working. So, picture this. Now, if we hit a ball, your ball is going to be at a certain position. Well, that position has a horizontal component, and it has a vertical component. Now, we're going to look at those independently with respect to time. So, our horizontal velocity is represented by this expression right here. This is the horizontal velocity, which is just the angle that it leaves the bat with relation to cosine times the actual speed or velocity. But what if there's a starting position? So these are the two equations we're going to be using today. Remember x of 0? Anytime you saw something with a 0 on it, this meant initial. So when you see x of 0, this is your initial horizontal position. Think of that word initial. Often we think of that as your starting position. Where do we start in terms of the horizontal movement? And then the horizontal velocity is going to be multiplied by the time. So if we take our horizontal velocity times time plus the start, that will tell us exactly where we are in our horizontal distance. Okay? Same thing here for vertical motion. Well, how far do I know, am I up or down? Well, it's based off of a couple of things. Now, this negative 16t squared, the negative 16 is actually gravity in terms of feet per second. Sometimes you saw negative 8.9, that would be meters per second. But then we have our vertical velocity, which is right here. We have our vertical velocity times time plus y of 0 is your initial, because of the 0, that's our starting or initial vertical height or vertical position. The nice thing is you don't have to memorize these. when you take the test, it's going to be open notes. I'll admit I don't have them memorized. I have to go back and look at the formula for each one. And in general terms, that's how we find our velocity or speed. And maybe, I wasn't going to write it, but I think that's also a good thing to put down here. So, there's a relationship that will tell us the position of a function, both horizontal and vertical. Okay, so let's look at how we apply these to context. You don't have to write all of this down. We're going to draw a picture just to make it make sense, and that way you don't have to write a full paragraph. And then we'll just identify the key pieces that we have. So, Brian Dozier, baseball player for the Twins, since retired. He didn't always play for the Twins, but he hit the ball when it's 3 feet above the ground. Well, let's stop right there. 3 feet above the ground. Is that horizontal movement or is that vertical? Vertical, right? We're going up. So that's your y value. That's y of 0. And maybe you want to write this off to the side as just things that we know. The initial value is 3 feet off the ground. Now, we also have an initial velocity of 110 feet per second. Okay, so that's the same thing as speed. I'll write that over here. Speed, which is the absolute value of the vector, is 110 feet per second. The ball leaves the bat at a 35-degree angle. It's important to note that we're talking about degrees here as well, not radians, because that would mean we'd have to change our calculator, but degrees. And then it says the horizontal, with the horizontal and the head towards, I'm supposed to say vertical, vertical, horizontal and vertical motion, head towards a 15-foot fence that is 340 feet from home. So we're going to take that and include that into our picture. So let's draw Brian Dozier. And then we know that we have a fence out here that is 15 feet tall. And I'll just tell you right away, this is definitely not drawn to scale. But what happens? Brian Dozier is going to hit a ball. And it's going to go up, and we don't know if it's going to go over. I don't know if it's going to hit the wall yet. I'm just going to, maybe I'll stop right there, because I'm not sure where it's going to actually go, but we know it's headed in that direction. And we know that the angle is 35. I should do that in blue. And we also know that the distance Brian Dozier is away from the wall is 340 feet. Now wait a minute, that's a horizontal movement, right? That's a motion horizontally, and that's basically how far we are away or how far the ball is the second it makes contact. And then we can say this is 3 feet here because that's roughly where he makes contact with the ball. Okay, now, what we need is the equation to figure out, does the ball clear the fence? Well, actually not y, we need y. If the ball clears the fence, that means we have to get higher than 15 feet. Well, to know if we get higher than 15 feet, we first have to figure out how far is the ball traveling. or in time. How long does the ball travel? Let's first do that. Now let's say how long is the ball in the air? We got to find the time. We got to find t. And then this is where we want to look at, we know exactly how far we're going to go in the horizontal position. So we know the x value, and we want to find, let's see, that I believe, and this is where I told you, I don't have this memorized. Nope, I wrote it on. Okay, so our horizontal position is the equation x bar, or x equals the speed times the cosine of t plus the starting point. Well, we know all that information except for we don't know the time. So we can find all the information here that we need. I'd love it if my highlighter worked. Well, let's plug in what we know. How fast is the ball going? It's going 110 feet per second. What is the angle at which the ball leads back? 35 degrees. And then where did we start from? Actually, it shouldn't be x of 0, sorry. X of 0 is where is the ball at time 0. So if I hit the bat with the ball, right at that moment, we have a horizontal distance of 0. It doesn't move. What this is, this 340 feet is our total horizontal distance. So that's what x has to equal. Well, now, if you notice, the only thing that I don't know is this value of t. Maybe I should put that in a different color. So it pops a little bit. That will give me the how long is the ball in the air. Right? We can solve this using math. And all I got to do is simplify. Now you could do all this in your calculator, but we have to be careful. I've got 110 times cosine of 35 degrees. So I need to move that over to the other side. So I'm going to divide both sides by 110 cosine of 35. And then in my calculator, you should put parentheses around the 110 times 35. Make sure you're in degrees mode. If you're in radians mode, it will change the answer. So go ahead and try this right now. Take 340 divided by 110 times the cosine of 35 degrees. And I usually round things to 3 decimals. So we know that at this spot of 340 feet. So when I go 340 feet, we know that it's going to take 3.773 seconds to get to basically the spot where it's either going to be over the wall or it's going to hit the wall. We don't know how high it is. We just know that's how long it's going to take to go in its horizontal motion. But we didn't answer the question yet. It says, did the ball clear the fence? Well, the clearing of the fence is talking about the vertical motion. Well, now we know how long it takes. We can use the fact, so this would be kind of the second step to this equation, is now let's find the vertical position when we know how much time has passed. That's the speed. That was given right up here. So the speed at which the ball leaves the bat. So that's your speed, 110 feet per second. And then the 35, the theta is the 35 degrees. That's the angle that the ball leaves the bat. And the 360 was how far we had to travel in total. Okay. So now, let's look at the vertical position, which is the y values. So we want to see, do we clear 15 feet? We got to go to this equation for vertical motion, which I'll just write down here. Plus y0. So that's our equation for vertical motion. But notice, we now know what t is. So we're going to plug t in every spot here. And then we also know that speed at which the ball left, so we're going to call that 110. We know the angle at which the ball left the bat, which is 35 degrees. And then we have y of 0. Remember what y of 0 is? That's your initial height. So when the ball hit the bat, we had an initial height of 3 feet off the ground. So look at, we know everything here. My answer is how high the ball is at the time 3.77 seconds. And we're going to find out, is this height higher than 15 or is it lower than 15? And clearly, this is just a sketch. So my sketch might be misleading. I don't know if it does clear or not. But let's plug everything into our calculator. And we're just going to simplify it. So you can go ahead and plug all that in. You can type it in exactly how you see it, using parentheses. I got 13.283 if I rounded to 3 decimal spots. And then it's important to think of the units. What is that? Is that seconds? No, because we already went for 3.773 seconds. This is referring to your vertical motion of how high up you went. So, what does that mean about my drawing? It's not accurate. 15 feet would actually be up here somewhere, because the ball is only going to go a maximum height, or it's going to hit the wall at 13.283 feet. So, to answer this question, does the ball clear the fence? No. It's going to be short by a couple of feet. It's going to be short by 1.717 feet. So, if so, how much does it clear the fence? You can't answer that. Because no, it doesn't clear the fence. If it doesn't, could the ball be caught? I don't know. That depends on, is it Byron Buxton? Maybe. Can he run and jump off the wall and get to 13 feet? There's NBA players that can't touch. Most NBA players can't even touch 12 feet. So this is to just catch it without using the wall. This is where you get to interpret it. Could the ball be caught? I don't know. If you justify somebody jumping off the wall and going to catch it, maybe. Most likely I would say no. That's really high off the wall. So what did we do? Let's recap quick. We took the information. We knew the initial height that the ball started when it was hit. That was 3 feet. We knew the speed, which is the absolute value of the vector, the magnitude of the vector. We knew the angle at which the ball left, which all of those fit nicely into our equations, and the only thing we didn't know was the time. So we used one of the equations to find the time, which the easiest one to do is the sine, because there's way less in its equation. So use the x value to find the time. And then once we found the time, we could use the time to determine the vertical height of the ball. Okay? So there's a lot going on, but it's a really cool application problem. Let's go back to our warm-up. What I'd like you to do is take this idea of Ben can sprint at a rate of 24 feet per second. Jerry sprints at a rate of 20 feet per second. Ben gives Jerry a 10-foot head start. Find the parametric equations that can be used to model this race, and then decide who would win. So what we're going to do is we're going to write the equation. Can you write an equation for Ben and Jerry that relates to parametrics? So let's look at this. Parametrics involve an x and a y component. So one of them had a rate at 20 feet per second. That's Jerry. And then Ben had a rate of 24 feet per second. But as we saw in the warm-up, Jerry got that 10-foot head start. We're going to give Jerry an extra 10 feet for his equation. But notice, this isn't a y equals x. It's relating back to time. And we did that in the warm-up. Well, what about the y values? What would they mean? And this is random. It does not have to be 3 and 5. But what we could talk about here is if I was to graph this, if this is the x location and this is the y location, that means that Jerry would start 3 feet away from something. Maybe this is the person that's saying, all right, on your mark, get set, go. Maybe that's the timekeeper. Jerry's 3 feet from them, and Ben would be 5 feet from them. And then what's going to happen is as time goes on, we're going to be able to tell how far they're running in a horizontal distance. Okay, so what I'd like you guys to do is we're going to actually go right back to kind of the work that we did last week with parametrics, because we need to figure out an XY table for both Ben and Jerry. Well, notice time x1, y1. Well, x1 and y1, this is the information that represents Jerry's output. Remember, x is the horizontal distance, y is the vertical distance. Now, it doesn't always have to mean horizontal and vertical. In this case, we think of this, they're not stacked on top of each other, right? This would be just a different direction. It's almost like taking an XY plane and laying it on the ground. We have to figure out the time. Well, what is Jerry's position? What's his horizontal movement at time 0, which is measured in seconds? And how about after 1 second, 2 seconds, 3 seconds, 4 seconds? And we're just going to go for 6 seconds here and see how far they go. Well, let's think about this. At time 0, where is Jerry? Well, if I plug 0 in for the time, 0 times 20 is 0 plus 10. Jerry is already at a 10-foot head start. But his y position is 3. Because that's what they say is the equation for y is he's 3 feet away from the person who's saying go. And then what about 1 second? Well, if I plug 1 in, 1 times 20 is 20, plus 10 is 30. But he's still running straight. So he still has a vertical distance 3 feet away from basically this x-axis. And then it's a linear model. Look, he can go up by each time. His rate was 20 feet per second. So you can quickly fill in the rest of these rates. Add 20, add 20. For every second that passes, he goes 20 more feet. So at the end of 6 seconds, he's 130. His y positioning doesn't move because he's running in a straight line parallel to the x-axis. He doesn't move. So let's look at Ben's information then. We're still going to go in seconds. Ben's horizontal movement is the x value. His vertical movement is the y. And the one constant between these two runners is time. Time is always the same thing. So then fill in this same work at time 0. Ben is at 0 feet away. Jerry was at 10 because he got a 10-foot head start. And then after 1 second, Ben is 24 feet away. And every second that passes, Ben goes another 24 feet. So we're just going to keep adding 24 all the way up. And then Ben's vertical position doesn't change because they tell us that he is always 5 feet away from the person that's keeping track of the time, or the person that says go. All right, so let's visualize this, because I think this is how we can actually see parametrics come into play. They each have their own equation. Yes, we could graph them, and that would give us, if I graph them on a regular XY plane, it would give us two lines that intersect, and it intersects right at 2.5. Right? If we were graphing the y equals. But we can't here because this is with respect to time. So let's look at this. If we look at Jerry, okay, Jerry says he's at 10 feet. So let's say here's 10 feet. After 0 seconds, this is where Jerry starts. So I might put a t equals 0 here for Jerry. Right? And then for Ben starts right here, and that's t equals 0 for him. And then if I go another, let's see, Ben goes 20 feet. So if I was 30 feet away, that would be Ben at 1 second. And then at 2 seconds, Ben would be at 50. And we could keep going, right? I don't want to get too crazy with this graph. But there's a way to represent his motion. Now, if we did the same thing with Ben would have to be at 24 after 1 second. And then he would be at 48. Those 48 is down here roughly after 2 seconds. And at some point, we're going to see the spot at which they are exactly the same distance away. We don't have to do this graph. This graph is just an extra little extension that I wanted to show you. But notice at 2 to 3 seconds, and between 2 and 3 seconds, all of a sudden, Ben passes up Jerry. And we knew from the warm-up at exactly 2.5 seconds, they were each 60 feet away. Okay? And that's where you can see, where's 60 going to be? Right at 2.5, we'll be right at 60. And right at 2.5, we're at 60. So parametrics can help us solve a problem like the warm-up just the same way we did before. All right, last one. And this one is not super tricky. We just got to think about what it means a little differently. And we're not going to do part D. All right, so what do we got? A famine relief drop. So a relief agency drops food containers from an airplane on a war-torn famine area. The drop was made from an altitude of 1,000 feet above the ground. Use an equation to model the height of the container during this free fall as a function of time. Wait a minute. Are they talking about vertical motion, or are they talking about horizontal motion? If something drops, is it moving left to right, or is it moving up and down? Moving up and down. So what we're talking about here now, we're talking about vertical motion. So we're going to talk about the y value, which was negative 16 t squared. This is, again, I always have to look. We're going to write an equation that models the height of the container during the free fall as a function of time. Now you notice they haven't given us a lot of the information that we had with the baseball problem, but yet we can still find that stuff out. What is the 1,000 feet in this problem? The initial height. Right? This is y of 0. It's your initial height. It's where the package is when time is 0. That's what that 0 means, initially. So I know that that is 1,000 feet in the air. Now, here's the key thing right here. The package is dropped. What is the speed of the initial package before it's dropped, or right at the time that it's dropped? Or maybe if I do this, if this is the package, right now, what is the speed of this? 0, right? It's not until gravity pulls it down. So if you see the word dropped, that's telling you that something started from rest, meaning it's not moving. So the initial velocity is 0 feet per second, which means that part is going to be 0. Now, do we need to know the angle? First off, it's dropped, but if I have 0 times anything, I don't need to know that angle that it's dropped at, because 0 times that is going to make it completely go away. And what's left over then is just gravity, negative 16 feet per second. So what equation would we have if we got rid of the fact that 0 times sine of theta is 0? We go right back to algebra 1, and we have a parabola that opens downward. If you were to graph this, there's your graph. It's dropping, and this would be time, and then we'd have to figure out at what time does it hit the ground. You could figure that out. We could plug in when y is 0. But what they want to know is, what about after 4 seconds? So after 4 seconds of free fall, the parachute opens. Well, how many feet above the ground will the food container be when the parachute opens? So all that's telling us is time equals 4. So we can figure out what that is by plugging 4 in, simplifying it, and that will be the height off of the ground after 4 seconds have occurred. So graphically, if my graph is at all accurate here, try to make it accurate. 1, 2, 3, 4. At 4 seconds, we would be 744 feet in the air. And then all of a sudden, any time after that, my graph actually past this graph isn't accurate because a parachute opens. And that's going to slow this way down. It might even bring it to be a linear model, because it might slow or fall at a constant rate. So the blue part of the graph down here might not be accurate, and that's actually creating what's called a piecewise function, because there's 2 different things going on. We've got the free fall versus the parachute. And the parachute is going to have a different effect on the graph. But what's the connection here? We can use this idea of vertical motion if we know the speed and angle and initial height. All right, so here's what we got. Didn't come through. And let's see if Schoology is working now. There's a link in Schoology, which I know it doesn't do good right now, but the homework tonight was on a pair deck. I don't love pair decks, so this is what I'm going to say. You guys can do this work and then submit it. I'm going to have you just submit your work, so you don't have to do anything on pair deck. You don't have to write the answers. You just treat this like it's a worksheet and submit your work. But it's 3 problems that involve a baseball problem, just like we did. They're going to have you write the horizontal and vertical component. And then we've got another baseball problem and another baseball problem. This one's interesting. The ball's hit straight up. But anyways, I might have to email that out if Schoology's not working. And hopefully by when we come back this afternoon, Schoology will be working and we can go from there.